Okay, good afternoon, everyone. We have Suraj Singh today with us. He is currently a postdoc at the University of Massachusetts at Dartmouth. He will be talking to us about baroclinic instability of curved oceans.
Thank you, sir. It's a pleasure to be back. Uh, this was my home for like 7 years, so it's really memorable time right now. So I'm going to be talking about the work that I've been doing in my postdoc for past 1 year, and we've been working on baroclinic instability, which is one of the most important instabilities which affect the global oceans, and it is one of the uh, key factors in the energy transfer in the global scale. So to start with, I'm going to show you this picture, which is one day. It's just a 1 day snapshot of Oscar currents. So it's a reanalysis product, and it is showing the horizontal kinetic energy in in, in the color. The most striking feature of this is that you can see that most of the kinetic energy is concentrated near the equator, which is to be expected because most of the energy is pumped into the global oceans near that place. And as you can see, there are branches of these kinetic energy going across through the Gulf Stream here and through the Kuroshio current near the Japan. And then there is a significant portion is near the Antarctic which is called the Antarctic Circumpolar Current. And these currents are literally littered with so many curved regions. So it goes to show that most of the kinetic energy is also associated with curved parts of the ocean, which is mostly eddies or meanders for the Gulf Stream or the Kuroshio. So a lot of the jets in the ocean, a lot of the velocities in the ocean are moving in curved regions, and hence really need to understand what happens due to the curvature of the flow. Uh, Another picture which goes to show what the curvature looks like around the globe is this. As you can see from the center near the equator, the curvature is very low, which is by the curvature low, I mean the radius of curvature is pretty high. So the flow is almost straight, but as the flow goes and then the energy is transferred from equator to the poles, it is transferred mainly through curved regions, and those are mostly called eddies or meanders. As you can see, the distribution of the radius of curvature around the globe, you can see that near the equator, the radius of curvature is pretty large. So for that, I would say the curvature is low, and you can see that the most of the curvature is near around 100 to 50 kilometer regions, as you can see from here. So it really needs to understand. We really need to understand what happens due to high curvature for the instability, which is the baroclinic instability.
So, what is the red and blue color?
Um, so this is the median and this is the mean radius of curvature. This is the median.
Radius of curvature of what?
Of the flow, horizontal flow velocity.
Flow velocity.
Yeah, it's the horizontal radius of curvature. There is a formula by which we calculate it, and I will show it to you later.
So it's completed from the fluid.
Yes, yes. It's completed
From the reanalysis.
from the reanalysis Oscar currents. It's called Oscar.
So it should be related somewhere to the actual curvature of the.
Yeah. But I mean, it's a formula which we use to find the from the as you can find the radius of curvature of a straight line through uh, basically from the u and v velocities, we try to calculate the radius of curvature.
I mean, he was saying something that it's not related to the radius of curvature of the Earth itself. So I was thinking that I mean,
No.
that's not what it is.
No. So it's the radius of curvature of the flow, the local radius of curvature of the flow, to be precise. And that is calculated from the local velocities and how much the velocity is curving in horizontal direction.
There is no connection to the actual.
The radius of curvature, no. For the Earth, no.
So what would it be in terms of how is it related? What does it actually signify?
So this basically signifies that near the equator, the flow is mostly straight in straight jets. And as we go away from equator to the poles, the energy is splits in form of eddies. And that's why we see so many curved regions here. And eddies are the primary regions of like the source of curvature. And another source of curvature is the meanders, which are the Gulf Stream and the Kuroshio.
So there is no correlation whatsoever to the fact that the flow on a curved surface.
Not directly, no, but there is a very big part which the radius of curvature of the Earth, radius of the Earth plays, which I'll come to that later.
Yeah, I think what you can also probably the way to say this is that you're looking at mean streamlines, looking at the curvature
Right,
of the
right.
streamlines.
Yeah, you're right.
That's basically what.
So this is just from the horizontal plane of the surface. But you're right. There is a role which the radius of Earth plays, and that with the basically the sphericity of the
Or the
flow.
rotation also, right?
Rotation,
Yeah, change.
yeah, exactly. Yeah, rotation will change as you go from equator to the poles, and that effect is predominantly present in direct regions. So in this picture, there are so many curved regions, and most of these curved regions are fronts. And fronts are which I'm going to talk about later in this next slide. So fronts, as you can, there is another picture that I'm going to show you. This is uh, sea surface temperature of one day in the Bay of Bengal. And as you can see, there are so many regions of very high lateral density gradients. So wherever you see a sharp gradient in the color, that shows that the waters are different. They are of different density. And these sharp lateral density gradient regions are called fronts. And these fronts play a very important role in distributing mass and distributing heat and distributing, and also are the regions of high dynamic activity. By that, I mean there are so many instabilities going on there. And that's why understanding these fronts are very important. Another reason why we need to understand this is because the global ocean models, they cannot go to this high resolution and still be able to run the simulation for the whole globe. So understanding processes at these small scales is important to inform the large scale models so that they are not way off the mark. And this is an ongoing area of research. So I'm going to show you a small schematic of this ocean fronts. So fronts are regions of sharp lateral density gradient. So whenever two different type of density of masses they come close to each other, you will see that the Picnock line becomes straight. By the Picnock line, I mean the constant density lines. And when it is like when it's very when it's vertical, it is prone to a lot of different types of instabilities that can happen there. For example, symmetric instability, for example, barogenic instability, which happens. But how do this lateral density gradient is sustained? As you can see from common sense that if you have a heavy flow here, a heavy water here along with side the light water, the heavy water will quickly flow beneath the light water and the light water will come above this. But this balance is maintained here. It's because of the Earth's rotation. And you can write this balance in a way uh, such that the vertical density gradient is related to the the vertical velocity gradient is related to the lateral density gradient. And this balance exists all over the globe. The only difference being that the term V by R is pretty small at the very large scale, as you can understand by the radius of curvature being very large. So that balance without the V by R is called the geostrophic balance. And that balance exists at very large scales, and it helps us explain what happens in the large Gulf streams or the Antarctic circumpolar current. But as you go towards the smaller eddies or smaller high curvature flows, the balance shifts to a cyclogeostrophic balance. Okay, now I'm going to talk about the paraclinic instability. We just learned what the ocean fronts are, and one of the instabilities that affect these fronts is the baroclinic instability. So baroclinic instability in an essence is just how the lateral density gradient adjusts itself. So whenever you have light water or light fluid on top of heavy, but it's in there is a lateral density which gradient which exists. Heavy water will always try to go below the light water, and the light water will try to go above the heavy water. But this process is stopped because of the Earth's rotation. So when this thing rotates, there is a balance which helps maintain this lateral density gradient. So this is a so then you have a situation which is stable, but that stability is broken by the baroclinic instability, and it's a process by which perturbations draw energy from the mean flow potential energy. So whenever you have it has a potential energy because the light water is still not completely above the heavy water. So this small the balance between the Earth's rotation and the lateral density gradients has an available potential energy which can be extracted by an instability, and baroclinic instability is the one which does that. So if you would understand that, then you would really you will see that baroclinic instability is the primary cause of instability in the global oceans, and it's a long wavelength instability. So we do not uh, you cannot understand it through maybe partial method. Uh, that's my opinion, but I still need to understand it in that way. And it's a shear driven instability because along with the lateral density gradient, you have a vertical velocity shear as well. So traditionally, baroclinic instability has been understood in terms of straight fronts and straight lateral density gradients. And it's the reason being that people think that even though the flow is curved in the oceans, the length scale of the flow is so large that the fluid parcel doesn't really experience the curvature of the flow. And hence we have these traditionally three different models of baroclinic instability. All of them consider the fronts to be straight. The two EDs and Charney's models basically talk about continuous stratification, fronts which are continuously stratified in the vertical and lateral. And the Phillips model helps us understand much more complicated stratifications by taking it piece by piece. So that's two-layer or multi-layer models. So I'm going to be considering only ED and Charney's model. I'm not going to consider the two-layer models. Now, what happens when a front is curved along with being laterally high lateral density gradient? This is the question we went on exploring, and we found this paper by Haza et al. In 2016, and it showed this is a picture from reanalysis. Also, it's not a real picture, satellite picture. It's a simulation product, and it showed lots of these undulations along the edges of this mesoscale eddy. And that got us to think that, okay, this is baroclinically unstable. This is a region of baroclinic instability to exist. But what are these things? So one thought would be like, what happens when a baroclinic instability encounters curvature? So that basic questions led us to this research. Maybe before going to okay. Maybe we come to that slide later. So to understand fluid at a global scale, we need to go to very small Rossby number. Rossby number is a measure of Earth's rotation, and a small Rossby number is the one where Earth's rotation dominates over the small scale forces of the flow. And we also have small aspect ratio, which would mean that the vertical extent is very small compared to the lateral extent. And even the vertical velocity is pretty small. So you can see that the flow is almost horizontal, but not quite horizontal. And there is a hydrostatic balance which exists in the vertical direction with vertical stable stratification. So and that leads us to these equations. This is the continuity equation where the vertical density gradient, vertical velocity term is small because of the Rossby number, and you have this balance as the dominant balance. And similarly, we have all the inertial terms are pretty small because of Rossby number, and the main balance is through the Coriolis and the pressure gradient. This is the horizontal velocities, and the vertical velocity is just the vertical hydrostatic balance, and that has been incorporated in these equations. And this is the density conservation equation. So we have these four equations, but we need to solve this for our case. What we try to do is we write an equation for the pressure perturbation in the polar coordinates. This is also important. So we can collapse all the four equations into one equation, which basically gives us the governing equation for pressure perturbations. Here, that is just the material derivative following the mean flow of the front. And f theta is the so we have the flow schematic is this. We have a mesoscale vortex, which is pretty large and has a radius of curvature r with a velocity v. And this is the flow balance which occurs. But in our case, I've taken this v square by r to be very small. That's because of the small Rossby number approximation. The Earth's rotation acts in the vertical direction predominantly, and that's what we consider. So confuse myself here. So this mesoscale flow is on the surface of the Earth, and the Earth rotates on its own completely. So the total rotation of the Earth acts upwards, but its components can be vertical and horizontal. What we consider is just the vertical component of the Earth's rotation. But that f, we call it f, the vertical rotation of the vertical component of the Earth's rotation. That f varies at every latitude, and it also varies in the vertical direction because of the because the latitude is changing. And but in the polar coordinates, we have f varies with theta as well as r, and that's the reason I have these two terms over here, which is f theta and fr. So in traditional geophysical flows, geophysical context, we will not see f theta or fr in this terms because they can consider this only in the Cartesian coordinates, where you have f varying only in the vertical, and that is called the beta term. But here, my coordinate system is centered towards the mesoscale vortex center. So the f can vary in theta as well as r direction. And that gives us this equation. Here, important thing to consider is the rotation of the beta effect from the Earth's rotation and the vorticity of the vortex appear together.
So FR is actually dou f by dou r.
Yes, it's FR is dou f by dou r, F theta is dou f by dou theta.
It's linearized, right?
Sorry?
The linearized it, material derivative.
Yes, that's the material derivative following the
Linearized. Yeah, linearized it, right? About V naught.
not sure about that.
So what is V naught then?
So V naught is the approximation of the lowest order in Rossby number. So
Oh yes, so it's an equation in V naught.
it's an
Yeah.
equation for P prime. Yeah, it's an equation V naught.
So what is the prime and why is P prime and V naught is not prime?
P prime is the perturbation. So prime terms are perturbations, and star is basically to say that
V naught is not a perturbation.
no, V naught is the mean flow velocity taken at smallest Rossby number approximation.
But that's also the perturbation, right? What we consider as the base state then.
No, that's the base state. The V naught is the base state.
Oh, so that's what I meant. So then you're
Yeah.
linearized about that base state, right? At this point, you've already
Yeah,
linearized.
yeah. Sorry, you're right. So we linearized about the mean flow along the front, and that's the V naught. And this is the material derivative following that the front velocity. And this is the equation for the pressure perturbation only. So we have removed all the T prime, V prime, and W prime components. So this is what I was saying. The beta is equal to FR, and this FR exists with the vorticity of the flow. This is very important for the next part. That's why I was stressing it. So for the next next operation, what we do is we are writing an equation for this for the mean flow around this mesoscale vortex. What we do is we now shift our attention towards one side of the eddy. Here in this case, I'm going towards the northern side of the eddy, and eddy is an anticyclonic eddy. So I'm converting from a polar cylindrical polar coordinates to a Cartesian coordinate now, which is centered towards the northern side of the eddy. Why am I doing this? Because I am taking the radius of curvature of the eddy to be large compared to the length of the front. And that's why I'm going from the polar coordinates to the Cartesian coordinates. This is such that the width of the front is very smaller than the radius of the curvature of the vortex. This basically results into the derivatives being given this way. Notice the negative sign is because in a cylindrical polar coordinate system you have anticyclonic to be positive, and in a Cartesian coordinate you have towards the east to be positive. So, and in an anticyclonic sense, this is a negative. This is the negative direction, and that's why the difference exists. You can derive this by converting the polar coordinate equations into Cartesian by doing the regular expansion into the velocity components, and then you take the limit for the theta to be equal to pi by 2, and then you will get the same relations. So that gives us wherever the 1 by r terms where they become large, and the derivatives become in terms of gamma, which is now the radial coordinate, and the kappa is the azimuthal coordinate, which becomes the x coordinate or the east-west coordinate in this way. And this transformation is important because this gives us an equation which can be compared to the traditionally known ED and Charney models, because they were written for Cartesian coordinate system. So if we remove this completely and this completely, what we will get is just this term, and this term with two boundary conditions will give us the two fixed boundary conditions will give us the ED model. If we have just this term, which is the beta term, planetary beta, and none of these, it will give us the Charney model. For our case, it's very interesting because we have this beta, the planetary beta along with the vorticity of the vortex. But this vorticity is now approximated for a large radius of curvature, and this is present along with planetary beta. So it basically tells us that the vorticity of the vortex and the beta plane act together for the Balanchine instrument. So they have a similar effect as what this way. Beta effect is primarily known to cause Rossby waves in the global oceans, and similarly for the vorticity. So I mean, they being present together indicates that the curvature can also give rise to Rossby waves. This is known in literature, but not in terms of curvature, but simply vorticity can cause the mean flow vorticity of the vortex can cause Rossby waves to appear around the periphery of the vortex. Another term, which is this is what it talks about is the vertical profile of the velocity, and that can also cause instability. So all these three terms can make the vortex unstable. What we are focusing on is just what's the effect of radius of curvature along with beta plane present, planetary beta present. So this contracts to this, which is a very simple equation, which is what we solve to get the relations. Here we basically go for Charney's model and not Edie's model, primarily because the Edie's model has two fixed boundaries and in the vertical, and that fixes the vertical scale of the modes. But in Charney's model, the vertical scale is fixed by the planetary beta, which means that these two terms will have a dominant effect. I mean, the instability will have a dominant effect due to these two terms. And what we find is that even the radius of curvature can affect the vertical scale of the modes. So we have this equation finally, and the boundary conditions are different. We just have a surface and an infinity boundary condition in the bottom. So the modes are basically surface localized, and they reach the bottom depending on the height scale of the problem. Now we solve this equation as a generalized eigenvalue problem using the Chebyshev collocation method. And so the tau is the parameter which signifies the radius of curvature. So a 0 tau will mean the radius is pretty large and it's a straight front. And as we increase tau, it means that the curvature is increasing more and more. And the first plot here is the growth rate versus the wavelength. The second plot is the phase speed versus the wavelength. So for tau equal to 0, which is the straight front, this is the classically known Charney growth rate. And we recover the same growth rate and along with the green modes. The most unstable mode is called the Charney mode, and the other modes are called green modes. So we recover those. And as we increase tau, we see that the Charney mode remains the same, but we have many more green modes appearing. Another thing which is important is that the growth rate doesn't change much. So what we see here is that the curvature makes it keeps the same mode, the Charney mode. It has the same growth rate, just that its wavelength is becoming smaller. And as we increase curvature even more, we see that the wavelength keeps getting smaller and smaller. That's one result that we have. The radius of curvature is in the denominator.
What is lambda is here? Capital lambda.
Lambda.
Not lambda, the other one. What letter is that? That's lambda.
Yeah, this shear, the surface shear.
So it's V naught Z.
V naught Z. Yeah. So F surface shear, the stratification, the planetary beta, and the radius of curvature is what gives us tau. The main thing is to notice that the tau is 0 corresponds to straight front, and tau not equal to 0 corresponds to curved fronts. So from here we know that okay, the what curvature is doing is it's reducing the wavelength of the most unstable mode, but it's keeping the growth rate to be the same. Then I plot the growth, the mode shapes in the along front direction versus the depth. So on the y-axis we have depth, and the x-axis we have the along front direction. And again for the 0 curvature or the straight fronts, we recover the traditionally known.
That equation would have closed form solutions for it.
Is there a reason why?
No, I'm saying, is there a reason why you're trying to do this numeraically?
Yes. So closed form solutions exist for beta only, and not of these terms.
So I'm saying the Boxley equation would have a closed form.
Sorry.
solution.
Yeah, it has a closed form solution, but not with tau square z term.
I'm saying even with tau from 0, it might have.
It might have.
Beta function is not. I don't know if it is particularly useful more than what you are doing is actually. But
Yeah, I mean it is solved for just one here, and using the confluent hypergeometric equation.
it will be like a Whittaker function.
Whittaker, yeah. I mean, yeah. So and it has a pretty lengthy solution. I'm not sure.
So the other thing is this is, I mean, at least the way you have mapped it, it's almost like a Couette flow on a beta plane that is varying in. So it's not really beta plane.
but it is like the planetary vorticity has a second correction.
A
So if you
second
have
correction.
a quick flow on a beta plane, that would have a constant by z minus c. But if you have a planetary vorticity that is also varying, then that's the kind of equation probably what you would.
Okay. Yeah, I mean, for quick flow, you'll have this term definitely
Yes, and
because
then
of,
on a beta plane, you would have it's like tau zero.
right.
So quick flow on a beta plane would be tau equals zero.
So that's the traditionally Charney mode, which we could
Yeah.
call it. Okay.
Which has, I think, solutions in terms of
Yeah.
Bessel functions.
Yeah. There were lots of. It was a pretty lengthy solution, and I was not sure if with this Z term pairing there would be any more clarity over there. So that's why we solved it numerically, and we just wanted to see what happens to the growth rate and the wave number itself.
So eta here is the growth rate.
Yeah. So I have used those terms to compare it to the literature, and but that is basically the imaginary part of the phase speed, and this is the real part of the phase speed. And with the wave number, the wavelength.
So what does it mean in terms of those very fine scaled dependence on the wavelength? You
Yeah.
see those like really rapid variations.
Yeah, I would say that there are more green modes appearing beyond this.
So this is the
three.
envelope of the most unstable mode, or is it one single mode that you show?
Traditionally, the largest mode is called the Charney mode,
Right.
and the other are called green modes. They have smaller growth rates, and the mostly they consider that the Charney mode will grow and the others will not grow.
So I'm just thinking of the cases of tau 2 and tau 1. You seem to have like really rapid variations
Yeah.
of the growth rate with the wavelength.
Yeah.
So is that I'm just imagining what does that signify? Is that one single mode which is unstable and it's varying in that manner?
It's tough
Or
to
do you have
say.
multiple modes which are becoming unstable at different critical wavelengths?
I think if we increase the resolution, we might be able to see that clearly. But till the resolution that I have used, it does not go down to zero and doesn't seem to be very separate.
No, it may not go to zero. What I was trying to say is that you have one unstable mode and you have a second unstable. The second unstable mode, if it is at a lower growth rate, at some point there is a crossover, and then basically,
okay.
so you see these very sharp variations
Yeah.
in the growth rate, and that is what I'm trying to understand. That is that for a single mode, or is that an envelope of multiple modes? Because especially if I look at tau equals 2, at the lower long wave limit, there seems to be like a very rapid oscillation that you have.
Yeah.
Suspect that should just be numerical.
I get it even after the high resolution. It doesn't seem to go away.
You solve this using Chebyshev correlation method, right?
Yeah. I've used around 600, 800 points, and I still get the same result.
So that's the reason why I was suggesting that it might be worthwhile to just check the analytical solution to
Right.
see, because when you do these things, whether you are getting one unstable mode or you're getting multiple unstable modes.
Yeah, that's
So
true.
it's because it's a really very an oscillation almost over one data point in wavelength.
Hmm.
I don't know if there are more data points there.
Yeah.
The green line.
Yeah,
It almost appears like it's one data point variation.
Yeah, that's true. But I think it's also because of the choice of the marker here. It's not doesn't seem to be very continuous. But my guess is that the largest one is still the same Charney mode, and the green modes appear much more frequently, and that's what we are going with. But it's worth understanding through the analytical. So for analytical solution exists for this the normal zero
One
case.
consequence of this would be that if you were to seed the system with disturbances in a wave number band in that region, the growth rate that it picks up can vary by a factor.
Right.
Because you have it switching between like 0.4 and 0.2 or 0.1. So in a very short range of wave number, because that's the numerical accuracy of the wave number with which you seed the system, you can see a dramatic change in the growth rate, which is I don't know. I mean, if that is expected, if it is indeed the case, then that is quite surprising.
Yeah, that's true. I mean, we haven't explained why it happens, and we were just focusing on the Charney mode, the most unstable mode. But it is worth investigating because even the growth rates for the green modes are also increasing. And if we go by that explanation, and it
Do you
does,
have the corresponding eigenfunction?
eigenfunction are not plotted, but
That might give you some idea of what's
oh,
happening.
yeah, you are right. So, like, if I can plot for these separate things,
Yeah.
that's
Can you
also-
show me again form of tau? What is tau exactly? So n, beta, r, all these are smooth, right? So
Yeah.
lambda s, what does it look like for your case?
Lambda s is just a value of the shear at the surface.
It's a constant.
Yeah, it's a constant. This is constant. This is constant. All are constants.
This is a singular equation, though, right? You have z minus c there, but it's singular
Yeah.
only near the
Critical.
so you shouldn't really see such rapid variation. So it is surprising. Maybe it's worth trying to figure out what's possible.
Yeah, that idea looks good. Like I can look at the eigenfunctions at that point and see the difference between the two. So this is the
So Suraj, you said the main one is the Charney mode, the other
Yeah.
one green.
green mode. Because he studied it. Yeah, some
So
green
what
studies.
comes, what the green color?
Oh.
I have about this.
True, sir. Yeah, I can paint them green and then. Yeah, that's true. And this is how the modes look like in the along front versus the vertical plane. So um, this is the depth, and this is the along front direction, and you can see the modes how they look like. For the tau equal to 0, which is the straight front, this is a well documented case, and you can see we recovered those. And as we increase the curvature, we see that the modes become much shallower, is what we see. We see that the modes are appearing at much closer to surface, and they're appearing in more numbers. So that means that the wave number is decreasing, or the wave number is increasing, or the wavelength is decreasing. So to compare with some results, we wanted to see how our mode looks like compared to the large scale modes and the small scale modes. So on the first chart here is, and we have also scaled the vertical coordinate and the amplitude and the growth rate and wave number in terms of the realistic values. So the first mode here, which is being compared, is the dotted line, which is the large scale ED mode. So to understand the large scale ED mode, you just think about the whole column of the ocean. The surface is one boundary and the bottom is another boundary. And there's a mode which goes from the top to the bottom, and that's the large scale ED mode. And we see that our mode appears at a much shallower level, and it has two peaks. There's another peak which happens below the surface. So our mode is shallower than the ED mode. How does it compare to the small scale, sub-mesoscale modes? The MLIs are the same kind of instability, but they happen in the mixed layer. There is in the ocean, in the upper surface, there is a mixed layer, which is of the very small, where the densities are mixed because of the work of the wind and constant heating and cooling, and that forms like a layer. There is the bottom mixed layer and this on the surface, and that has a very shallow mode. And we see that our mode is not that shallow. It's still, it goes deeper than the mixed layer. So what we want to say is that our mode, because of curvature, there's a mode which exists which goes below the mixed layer, but it's still shallower than the large scale ED mode. To compare with these, the growth rates of these, we have plotted. This is a little difficult to show because I'm showing the high growth rate MLIs as well as the low growth rate ED mode. On the y-axis, we have growth rate in terms of per day, and we have on the wave number in the per meter. So very small wave number means very large wavelength, and there are like very large scale instabilities. And this dotted line is on the left is the large scale ED mode growth rate. You can see it's pretty small. It's around 0.0, 0.026 per day, and that grows very slowly. We see that our tau equal to 0 case lies almost exactly around that region, about the same highest growth rate. So the largest for the straight front, the Charney growth rates lie in the same ED growth rate ranges. But for a higher curvature, we see that the largest growth rate happens much further at a very small wavelength. So this is like a link between the large scale. This could be they could be performing in between the very large scale and the very small scale, which are the MLIs, but the growth rates of them are the same. So we can think about them as the large scale growth rate, large scale beast, but they are appearing at a very small wave number. And this is the result that we are trying to show that we have found. Another implication of this.
So what is that result that you are comparing? Some numerical result
Yes, that's a numerical result.
for the same system?
So what they consider barometric instability for two cases. First is the mixed layer case and for the whole ocean column. And they do not consider any sort of like variation in velocity because of like curvature or any sort of like even for a linear shear flow in the horizontal. They just have a simple front which goes throughout the ocean column. The vertical scale is throughout the ocean depth, and for the second MLI is just the vertical scale is the mixed layer depth. So both are ED cases. They're not Charney cases. Charney cases are different because there's a slide that I skipped, which helps explain how Charney and ED are different. Charney modes are basically surface localized or bottom localized because it doesn't need the whole depth to be fixed, and the depth scale is given by the PV gradient here, and that I showed here. So the PV gradient or the B or the FR, this whole thing can dictate the vertical scale of the Charney mode, and that is why we have with curvature the the vertical extent of the modes keep varying because of the curvature. Here, what I'm plotting is the along front averaged buoyancy flux. Why do we want to know buoyancy flux? So what it tells us is how much of the buoyancy is being pulled up from the ocean and being mixed because of this parametric instability. So for a straight front, you can see that the mode goes very deep, and the magnitude is not that much. So it pulls. So it's like a very slow churning, slow churning, overturning, which is happening. But as we increase the curvature, we see that the mode shapes, the scale depth of the modes are reducing, and you can see that for the highest curvature, even the amplitude is pretty high. So even
What
though
is the averaging you're doing here?
this is the along front averaging.
But how do you do an average here? Do you have any simulations or?
No. It's from the numerical results itself. But I mean,
You're averaging over what? You're just solving the eigenvalue problem, right?
yeah. So one wavelength, two wavelength. I mean, it doesn't really make sense because it will give us the same result. But this is what we want to compare to because we want to compare to the similar values in the simulation. So to show that.
But I'm just wondering what exactly this represents. So this averaging that you're doing, you said you do it for one wavelength and then another wavelength and then average across different.
Like 5 wavelengths and then divide by 5. Basically, it will not change because we just an eigenvalue problem, so not true. But this is the quantity which we compare to when the simulations have this quantity and they compare and they talk about the results. So we wanted to compare with them. And so in the first slide, what we talked about was how the ocean fronts are everywhere in the oceans, but they are at such a small scale and they appear at such sharp density gradients that they are very difficult for the global ocean models to resolve. And what helps then is
Just one question. Here in the previous slide, when you have the comparison of the growth rate, with wave number. Do I understand this in the same way as you had it in the previous plot, where
Yeah.
you show the variation with that?
Yeah. Yeah,
So
so
it doesn't necessarily have those very fine scale features that
it has. It's just been stretched.
saying on that scale, it's not really visible. It's exactly the same. plot
Yeah,
that you
it's
showed
exactly
us-
the same plot.
Same plot that you showed us earlier.
Yeah, you can see the difference between, because this is a wave number plot, and that was the 1 by wave number plot. So that's the wavelength.
Although
And
this is non-dimensional growth rate.
yeah, it's non-dimensional growth rate, non-dimensional
The
wavelength.
features are
Features are still
visible on that
Yeah, and also the tau is
same tau, right? Tau two is
no, it's tau will 3 also, so it's much higher. So yeah, that's
So
it.
you just see even finer features.
Yeah, it's even finer features, but they are spread over. They happen at different wavelengths, and that's why in this log plot it is stretched.
So tau basically increasing means you have more curvature.
More curvature.
But and you know why more curvature actually gives rise to such a phenomenon.
Yeah. So the main thing is, main thing to note about from here is that the curvature controls the depth scale, and as the depth scale is controlled, even the horizontal scale, it reflects in the horizontal scale. So smaller depths result in smaller horizontal scales as well. I'm not sure how this exactly explains it, but it does. So what we know is that it controls the vertical scale, right? And what controls the vertical scale is also the planetary beta. Overall, what basically controls the depth scale is the PV gradient, and this whole thing is the PV gradient in this problem. So curvature appears along with the other PV gradients, and as we increase curvature or decrease this R, we basically get that it has the same effect as increasing planetary beta, or it has the same. I'm not sure about what effect does this.
term which replaces the tau. There's in a combination of terms there.
For the
The
tau,
first line to the first line where you have the equation
Yes.
to the equation at the bottom.
Yeah.
Where you have
Yeah.
the tau term.
So there is a trick here. What we do is we want to simulate the traditionally understood like a uniform velocity which is going along the front and has a simple density gradient. Just the fact that it is slightly curved is what makes it different. So we wanted to go towards the ED model and slightly a small curvature approximation for the ED model. So what that tells us that then when the velocity is uniform, this term will drop out, this term will drop out. So only this term will remain. And this term alone is appears in tau. So tau square will give us velocity square and velocity. Okay, there are more but it will give us RC square, which appears here, and that's the only term which is active here. In fact, this is the only term which adds to the planetary beta, and not these terms. These terms will reduce the effect, which is what's happening. It has been known traditionally in terms of that the horizontal shear decreases the baroclinic instability. That is known in the literature. It's called the barotropic governor. We see that even here, the horizontal shear is decreasing the effect of the planetary beta or the baroclinic instability. So this is why the curvature helps increase the effect of beta, the planetary beta. In fact, the reason why it compares very well to planetary beta is something that how the planetary beta itself appears in the equation. To understand planetary beta, what we do is we have a fluid the expressions for equations of fluid on a sphere, complete sphere, and what we do is we approximate along a single latitude, and that gives us the local gradient in the planetary rotation, and that gives us the beta effect. So our analysis is similar to the beta effect which appears on the large scale of the Earth's surface. We are doing it on a circular vortex, where we are focusing on one simple region, and that gives us the PV gradient which appears because of the Earth because of the curvature of the vortex. And this analogy is what helps us explain why the PV gradients can appear because of Earth surface, the rotation, the curvature of the Earth's surface, as well as the curvature of the mesoscale vortex. And this is why we get what we see here. And the fact that the because of this relation tau, we can find out how much from the Earth's rotation, Earth's beta can the radius of curvature give, like according to how much. So basically, tau equal to 0 compares to the just the Earth's planetary beta, and as we go, we see that we can get up to tau equal to 10. We have found that if we find because of the radius of curvature plots along the from the first plot that the second plot that I showed, we can find out what are the tau values that appear along across the globe, and we find that tau can become really high. And
But till what tau would this equation be
Yeah.
valid?
so that's another excellent point. So the only constraint that this equation has is the small Rossby number, and as we reduce tau, which means the radius of curvature becomes small and small, the centrifugal forces become more strong, and that basically breaks the quasi-geostrophic approximation. So Rossby number will not be very small anymore. Another
What I was thinking is that is this equation exact in a curvature radius coordinate system? You have designed a new, if you go to the previous slide, you have a coordinate system which is in terms of gamma, which is the
Yeah.
radius,
Yeah.
and the curvature up,
yeah,
right? So now
curvature is RC, kappa is not. Sorry for using the
RC
same.
would be radius of curvature, right?
Yeah, kappa is the coordinate along the.
Oh,
it's
okay.
just the
So that's the curvature equivalent to a curvature or arc length rather.
arc length.
So you have this new coordinate system which is using. The next equation is that exact on for the entire sphere surface for arbitrary theta, or is it
You mean
limited
the-
to a small angle?
You mean this?
Yeah.
Yeah. So that's an important point because this is only valid
No,
for.
the previous one, the previous equation.
Oh,
Yeah.
this.
Yeah.
Yeah, this is valid for all theta.
Okay.
Yeah, this is valid for all theta.
And what about the one you had later in gamma and kappa?
Yeah. So because of these relations will appear differently if we go to minus pi by 2, because then the Cartesian coordinate notion and the anticyclonic flow both align in the same way. So you won't get this minus anymore. So there will be some differences. What I found that this term is different and rest of the terms are same. So there is some difference when we go to when we focus at different regions in this. There's another reason why it will be different is because you will have terms from f theta appearing and f r appearing. Because right now we are focusing on only the northern part, so there's f only varies in the r direction, not the theta direction. But if I focus on this part, then f will vary on theta direction as well. So this equation is exact, but the other equations we will have to derive from different parts of the vortex. All right, I think.
So Suraj, there is a class after this, okay?
Yeah, I think I'm.
Rest of time.
Yeah, I think I'm done. So this is the last one, and this is the conclusions. This is what we have found. And the references if someone wants to make, and any questions if you guys have, we're happy to take.
Thanks, Suraj. And for some questions, someone was joined online. If you have questions, you could either unmute and ask, or type your questions in the chat box. While we wait for those questions, are there any questions from the audience here?
So are you also working on any simulations to this?
Yes. By the way, I wanted to show you some simple simulations also, but we have like some preliminary simulations to show, and this is a simulation which is used, which is done in Oceananigans. This is an example of a simple baroclinic instability for a straight front. You can see that the isopycnals are becoming shallower, much more inclined from a very vertical position. And this is the case for a straight front. And I wanted to show for a curved region. So this is a very preliminary simulation, and you can see that there are differences from a straight region, which is in the middle, and the curved region in the outside. So this was the inspiration for us to keep going. Okay, yeah, there could be a difference between curve and a straight region. But this is not an exact simulation that we want to show, but it's just a preliminary analysis.
Thank you. Okay, let's thank Suraj once more.